This is part 1 of Module 7, where you will be introduced to the bipolar junction transistor. This is what I plan to cover in this particular lecture. First, we'll take up the simplified construction and circuit symbols for a BJT. Second, the modes of operation of a BJT. And finally, we'll how to perform DC analysis on BJT circuits. Before I can explain to you the simplified construction of a BJT, let me provide you a simplified construction, the simplified construction of a diode. There are two types of semiconductors based on what type of charge carrier predominates. You have your N-type semiconductor where your charge carriers are predominantly negative, and your P-type semiconductor where your charge carriers are predominantly positive. A diode is formed by creating a junction between an N-type and a P-type semiconductor. Okay. So this is how a diode is formed. I have an N-type semiconductor here. I have a P-type semiconductor here. Okay. Somehow we fabricate the device so that there is a junction between the two. We now call this your PN junction. To your P-type, you attach a terminal and you call that your anode. To your N-type, you attach a terminal, you call that your cathode. So this is equivalent to what we already know to be the junction diode. Okay, what does a BJT look like? A BJT contains two PN junctions. So there are two possibilities. First, you have your PNP transistor, where you have an N-type sandwiched between two P-types. Okay. To this P-type, we attach a terminal, we call that your emitter. Here, we attach a terminal, we call that your base. And here, we call this your collector. Notice that you will have two PN junctions. You have a PN junction between your emitter and your base. And you also have a PN junction between your collector and your base. So you call this your emitter base junction, you call this your collector base junction. Now the other possibility is when you have a P-type that is sandwiched between two N-types. Now these are still called your emitter, your base, and your collector. This is still your emitter base junction, this is still your collector base junction. So these are your two different types of bipolar junction transistors. We call this your PNP transistor. You have a P and then an N and then a P. And we call this your NPN transistor where you have an N, then a P, then an N. Okay, here are the circuit symbols. This is the circuit symbol for a PNP. Notice that you have an arrow from the emitter going toward your base. The arrow is the direction of current flow when your emitter base junction is forward biased. So imagine this to be a diode from your emitter to your base. When that is forward biased, what direction will the current flow? It will flow from your emitter to your base. That's why your arrow is pointing in this direction. If you take a look at the circuit symbol for your NPN, the arrow is pointing from the base toward the emitter because that is the direction of current flow if your emitter base junction is forward biased. It will be from P toward the N. Okay, let's take a look at your NPN transistor. So you have two junctions. You have your PN junction here and you have your PN junction there. At first glance, this is what it looks like. So you have a diode from your base to your emitter, and you have a diode from your base to your collector. So it appears like two back-to-back diodes, where you have access to the interconnection between the two diodes. Under normal circumstances, current cannot flow from C to E. For example, if I put a voltage source here in this manner, okay, So this voltage source is trying to push current in the clockwise direction. However, that current will be countered by your collector to base diode, because this is going to be opposite the direction of the current. So current will not flow. If I invert my voltage source, then it is this diode that will counter the current. So either way, current will not flow. So under normal circumstances, current cannot flow from your collector to your emitter. Okay. In an actual transistor, however, the base region, this particular region, is very, very thin. It's very, very thin. This is a little bit exaggerated. This should have been drawn maybe only as a line. And under the correct conditions, electrons from the emitter may emerge at the collector. If I have electrons flowing into the emitter, into the N region here, because this is very, very thin, under the correct conditions, those electrons can emerge at your collector. And that will constitute a current from your collector to your emitter. Because note, electrons flowing from left to right will constitute a current flowing from right to left. Now, we're not going to explain in EEE 123 the physics behind this. So you're just going to have to take my word for it at this point in time. Now, these are the reference directions for the current for a PNP and an NPN. Note that for a PNP transistor, the bulk of your current from your emitter will emerge at the collector with a small amount of current coming out at the base. So your current flowing inward here, then the bulk of that will flow out this way, and some current will flow out into the base. In your NPN, the current directions are the opposite. You have your emitter current consisting of two components. You have most of it being the collector current here, with a small amount of that being contributed at the base. In either case, your emitter current is going to be equal to your base current plus your collector current. In other words, your transistor satisfies Kirchhoff's current law. If you consider this to be like a box, you don't know what's in the box. You know that because this cannot accumulate charge, the charges that enter that particular box somehow has to go out. And that's why the sum of your currents entering the transistor must be equal to the sum of currents leaving the transistor, or you have this. Now, what are the different modes of operation of your transistor? That will depend on whether your emitter base junction is forward biased and reverse biased, and whether the collector base junction is forward biased or reverse biased. So you have four possible combinations. When both your emitter base and your collector base are reverse biased, we say that your transistor is cut off. When your emitter base is forward biased and your collector base is reverse biased, we say your transistor is in active operating mode. When it is the opposite, your emitter base is reverse biased and your collector base is forward biased, we say you are in reverse active mode. If the transistor were symmetrical, and the way we drew it earlier was it is symmetrical, the way I draw it here, for example, this shows you a symmetrical construction. In other words, this and this are equal in form factor. If your transistor were symmetrical, then this mode and this mode should be the same. But in reality, your transistor is not symmetrical. In reality, and you're going to see this in EEE 131, your emitter area is much smaller than your collector area. And therefore, it will not behave the same way when your emitter base is forward biased and your collector base is reverse biased, or when your collector base is forward biased and your emitter base is reverse biased. It will not behave the same way. So you call this the reverse active mode. No? This reverse active mode is normally not used. In fact, your transistor only goes in reverse active mode when you make a mistake, probably in making the connection. If you inadvertently interchange the emitter and the collector terminals. Okay, the last operating mode is your saturation mode. And this happens when both your emitter base and your collector base are forward biased. So what are the different models of your transistor for the different operating modes? So we have 3 operating modes here where your transistor is normally used: your cutoff, your active, and your saturation. When your transistor is cut off, when your transistor is cut off, both your emitter base and your collector base is reverse biased. In other words, from emitter to base, you have an open circuit. From your collector to base, you have an open circuit because they're both reverse biased. So this is now your equivalent circuit. You happen to have a diode here, no? You have a diode here, you have a diode here, but because they are reverse biased, there is no conduction, and therefore your currents are equal to 0. No? So you have IB, which will be equal to IC, which will be equal to IE, will be equal to 0. And it's the same for an NPN, and a PNP. The same model. When do you use your BJT in cutoff mode? Typically, that is used in digital circuits and in switching applications. So we're going to show examples of switching applications later on. On digital circuits, we're going to show this when you go to, I guess it is module 9 or module 10, when we take up digital circuits. Okay, the second operating mode is active mode, and this is when your emitter base is forward biased and when your collector base is reverse biased. In this particular case, your transistor can be modeled by a current-controlled current source. For an NPN, this is my transistor. Okay, you model that as a current-controlled current source, where your collector current is actually IB, your base current, multiplied by a parameter beta. Beta is a parameter of the transistor. Okay. So you have to solve for IB, and after solving for IB, you multiply that by beta, and that will be the value of your IC. How do you solve for IB? Well, you can use the piecewise linear model of the base emitter diode. So you can use the piecewise linear models you can apply the piecewise linear models to the base emitter diode so that you can compute for IB. And once you've computed for that, automatically you will also now know what IC is. So this is for an NPN. When we draw the PNP transistor, usually we draw the emitter on top and the collector below. We draw the emitter on top and the collector below. The reason why we do that is because for a PNP transistor, the collector is usually at a lower potential than the emitter. That is so that current will flow from emitter to collector. The collector has to be at a lower potential than the emitter. And usually when we draw things, we like the lower potential nodes to be at the bottom and the higher potential nodes to be on top. In fact, we always draw the power supply on top, and we always put the ground connection at the bottom. So if we follow this convention, then this is going to be our model. Okay, so your diode is from emitter to base. Okay, and your current here is from emitter to collector. So this is equal to beta times IB, where this is the value of IB. Again, you can use your piecewise linear models to compute for I sub B. If your base emitter is conducting, so if this is conducting, remember we said that a forward bias does not necessarily mean conducting, because it can be forward bias, but if the voltage does not exceed the threshold voltage of the diode, you will have practically no current. Okay, but if the base emitter diode is conducting, then the voltage from base to emitter, we just call that VBE active. And for NPN, that will be 0.7 volts. Now, if your base emitter here in your PNP is conducting, then the voltage across that will be VEB. No? Take note that we reverse the subscript. No? So here it is VBE, here it is VEB. But likewise for silicon, that will be approximately equal to 0.7 volts. So this is the model of your BJT in active mode. Now, what about in saturation mode? In saturation mode, both the emitter base and collector base junctions are forward biased. In saturation mode, the emitter base diode must be conducting. So if the emitter base diode is conducting, then automatically it can be represented by its constant voltage source model. So for an NPN, that would be VBE SAT, which for silicon would be 0.7. And for a PNP, we have to reverse the subscript. It's going to be VEB SAT, which is approximately equal to 0.7 for silicon. And in saturation, your collector to emitter voltage will be practically constant, okay? And that value will be VCE SAT. For your PNP, it's going to be VEC SAT. So you just reverse the subscript. So this is what happens when the emitter base and the collector base junctions are forward biased with the emitter base diode conducting. The model is really just two. Okay, the simplified model is really just two constant voltage drops. One from the base to emitter and the other from the collector to the emitter. Okay, in saturation, what are these values? For silicon NPN transistors, VBE SAT is 0.7. On the other hand, VBC SAT is approximately equal to 0.5. You might say, why 0.5? Shouldn't it also be 0.7? Well, it has something to do with the way the base collector junction is constructed. It's not constructed in the same way as your base emitter junction, and there will be a change in your junction voltage. It's going to be 0.7. So if you take a look at the NPN transistor, so let me draw the NPN transistor here. Okay, VBE SAT, this is going to be 0.7, 0.7 volts. On the other hand, VBC SAT, so it's from base to collector. Okay, this is going to be 0.5 volts. If I wanted now to get this voltage, which is VCE SAT, okay, if I apply KVL, VCE SAT will be equal to VBE SAT, okay, minus VBC SAT. Remember, this is VBE SAT. That's 0.7, and this is VBC SAT, which is equal to 0.5. And what is this going to be? This is going to be 0.7 minus 0.5, or 0.2 volts. Right? So this voltage for silicon is going to be 0.2 volts. Now, if you take a look at the PNP VEC SAT, so again, we just reverse the subscripts, that will be equal to 0.2 volts. That is your model in saturation. So we already have a model for your BJT in cutoff, a model in active, a model in saturation. We can now go ahead and solve or do DC analysis on BJT circuits. Okay. By the way, if the transistor is saturated, increasing I sub B will not increase I sub C. I sub C will be equal to IC sat, which is determined by the connected circuit. You're going to see this later on. And well, it's also apparent here. This I sub C will have nothing to do with this I sub B, because what will dictate this I sub C is just this particular voltage. Regardless of the value of I sub B, this will just be dictated by VCE sat. Okay, so you're going to see that later on. By the way, these are some useful transistor current relationships. So we said that Kirchhoff's law is satisfied by the transistor. So you have IE is equal to IB plus IC. We also know that in active mode, IC is equal to beta times IB. This is in active mode. If I substitute this, for example, into this, what am I going to get? I'm going to get IE is equal to IB plus beta IB, or 1 plus beta times IB. Okay, so that's this. That's IE. If I know IE, I can solve for IB, which is just this. So I just transpose. This 1 plus beta becomes the denominator on my left side, and I now have an expression for IB in terms of IE. On the other hand, from here, I know that IB is equal to IC over beta. And this I can substitute into this. If I do that, what am I going to get? I'm going to get I sub E, okay, is I sub C over beta plus I sub C, okay, which is going to be I sub C multiplied by 1 plus beta over beta. Okay, that is this expression here. So if I'm given I sub C and I know beta, I can easily get I sub E. On the other hand, if I know I sub E and I know beta, I can get I sub C by transposing. So you're going to get now this equation. So these are useful current relationships. Although, what you really just have to remember is this. IE is equal to IB plus IC, and this. IC is equal to beta times IB, and you can actually derive all of these different relationships. So let's now go into the DC analysis of BJT circuits. I have simplified this into 3 steps. The first step is determine if the base emitter junction is conducting by applying KVL to the base emitter loop in the same manner you would analyze a diode circuit. In other words, the base emitter diode you can replace with its piecewise linear model. Usually what we use is the constant voltage source model. And when you use that model, you can determine whether the base emitter junction is conducting or not conducting. If you find that the base emitter junction is not conducting, then automatically you know that IC is going to be equal to 0, and also that IE will be equal to 0, or the transistor is cut off. So you just now replace your transistor with its cutoff model, and you can proceed to analyze the circuit. However, if the base emitter junction is conducting, then you have to go to step step 2. In step 2, your base emitter junction is conducting. We're either in active mode or saturated. Usually, we assume that it is in active mode, and we replace the transistor with its active mode model. Now, after replacing the transistor with active mode model, we compute for VCE. If it's a PNP, we compute for VEC. If VCE is greater than VCE SAT, then the assumption that the transistor is in active mode is correct, and you can proceed with the circuit analysis using this active mode model. Otherwise, the transistor will be in saturation. No? When is the transistor in saturation? If the VCE you computed here is going to be less than VCE SAT. Because VCE SAT is the minimum voltage that can exist between your collector and emitter. It cannot exist at a smaller voltage than VCE SAT. So that is the minimum voltage that can exist between your collector and emitter. If you find in your computation here in step 2 that you computed for a smaller voltage, then that means that your transistor is already in saturation. You replace the transistor with its saturation mode model, and then you proceed to analyze the circuit. So what better way of illustrating this than through an example? Okay, so here I have an NPN transistor. Okay, you have a base resistor connected at the base, a collector resistor connected at the collector. We apply our power supply here, VCC, in this particular case 5 volts. We apply our input here, okay, at the base resistor, and we get our output here. No? In this particular case, V out is equal to VCE. Remember, this is my collector, this is my base, this is my emitter. So therefore, this is equal to VCE, which is equal to V out. Okay, so I'm supposed to determine V out for 3 different conditions: when V in is 0.5, when V in is 1, and when V in is 1.5. Okay. So let me start with letter A. No? V in is equal to 0.5. No? So I apply that now to my input terminal. Now what's going to happen? Okay. For my base emitter to conduct, the open circuit voltage between my base and emitter should be greater than the cut-in voltage or the forward voltage of my base emitter diode, which is approximately equal to 0.7. You imagine, you imagine the equivalent circuit, your base emitter circuit, no? Your base emitter circuit looks like this, no? You have V in, I have RB, and I have a diode. And the forward voltage of this diode is 0.7 volts. Okay. For this diode to conduct, the open circuit voltage across it should be greater than 0.7 volts. Right? That's method 2. No? We assume that the diode is an open circuit. Okay, we get the open circuit voltage. If that open circuit voltage is less than V sub F, then the assumption is correct. But if it is greater than V sub F, then the assumption is wrong. So here, 0.5 is less than 0.7 volts. No? Therefore, this current I sub B will be equal to 0. Or the transistor is cut off. BJT is cut off. Okay, if the BJT is cut off, I sub C is also going to be equal to 0. Now, what is V out? V out, okay, V out is VCC minus ICRC. But this is 0. So V out will just be equal to VCC, which in this case will be equal to 5 volts. No? So for letter A, V out is equal to 5.0 volts. That's how you solve for letter A. Okay, let's go to letter B. Letter B, V in is equal to 1.0 volts. Okay, again, no? Let's apply V into our base emitter loop. No? So, my base emitter loop, okay, I have V in, I have RB, and then I have my base emitter diode, no? Whose forward voltage is 0.7 volts. No? This is 1.0 volts. Okay, it's very easy to see that I will get a current that will flow, IB. No? In fact, IB is going to be equal to V in, okay, minus 0.7 over RB. Okay, so this is going to be 0.3 over, what is RB? RB is 10K. Okay, 0.3 volts divided by 10K is 30. This is going to be 30. Yeah, 0.3 over 10 is 0.03 or 30 microamperes. Okay. Okay, so we know that I sub V is going to be 30 microamperes. So let's assume transistor is in active mode. Meaning to say, IC is equal to beta times IB. No? So take note that this formula will only work if you're in active mode, because it's only in active mode where your transistor is a current controlled current source. Now our beta is equal to 100. Okay. So what does that make IC? IC will be equal to 100 times 30 microamperes. I'm going to get 3 milliamperes. 3 milliamperes. Okay. So what is going to be V out? No? So V out is going to be VCC minus IC times RC. No? VCC minus IC times RC is V out. So this is going to be 5 volts minus 3 MA times 1K. And I'm going to get 2 volts. Now I have to test. No? Is VCE greater than or equal to VCE SAT? No? My VCE SAT is 0.2 volts. Yes. No? Because 2 volts is greater than 0.2 volts. No? Therefore, my assumption is correct. And therefore, my V out is correct. V out is now 2 volts. So here, V out is equal to 2.0 volts. Okay, what about letter C? V in is equal to 1.5 volts. Again, no, my base emitter loop, okay, I have 1.5 volts, RB, here VF is equal to 0.7. So again, it's easy to see that IB is going to be greater than 0. No? IB is going to be 1.5 minus 0.7 divided by RB, which is 10K. No? Yeah, divided by 10K. And I'm going to get 80 microamperes. And IC is going to be 100 times 80 microamperes. No? That's beta times IB, which is going to give me 8 MA. Okay, so this is assuming, no, this is assuming active, no, assuming active mode. Right? Because it's only in active mode where we can use the formula IC is equal to beta times IB. So assuming active mode, what is V out going to be? This is VCC minus ICRC. Okay, that is 5 volts minus 8 MA times 1K. I'm going to get negative 3 volts. Okay. Note, okay, V out or VCE, because this is equal to VCE, okay, is less than VCE SAT. Remember that VCE SAT is the minimum voltage that we can have across our collector emitter terminal. Now we're getting VCE, which is less than VCE SAT. And therefore my assumption is wrong. The transistor is saturated. If my transistor is saturated, I now apply the saturated model. In my saturated model, VCE should be equal to VCE SAT, no? Which is equal to 0.2 volts, which is equal to V out. No? So here, V out should be equal to 0.2 volts. Okay. Now you will notice that, for example, if I try to plot V in, V out, no, V out versus V in. Okay, when V in is equal to 0, what was my V out? My V out was equal to 5 volts, no? Okay. When V in is 1, when V in is, let's say 1 volt, no? So let's say this is 0, that's 1 volt. I notice that my V out, okay, V out is equal to 2 volts. So it went down, no? From 5 volts, let's say we're now here at 2 volts, no? 2 volts. So as you increase V in, this goes down, no? Now when does this stop going down? This will stop going down when the voltage V out becomes equal to VCE SAT. No? This is VCE SAT. VCE SAT is the minimum voltage that can exist between your collector and emitter. Okay? And from that point onward, okay, my output will remain at VCE sat. In other words, as I increase my input, my output goes slower, but at some point, it will hit VCE sat, which is the minimum value that you can have, and further increasing Vin will no longer make my output any smaller. Now, when does that happen? When does that happen? Okay. Saturation occurs, okay, when IC is equal to IC sat. And what is this? No? This is VCC minus VCE sat over RC. No? So this is the minimum value that your VCE can have. Okay, this is fixed. This is your collector current. Okay, so this is when saturation will occur. No? When IC is equal to IC sat. In this particular case, that is 5 minus 0.2 over 1K. So that will occur when IC is equal to 4.8 MA. No? When will you get 4.8 MA? No? You get 4.8 MA when IB is equal to 4.8 divided by 100, no? Or 48 microamperes. 48 microamperes. No? Okay. In other words, if we increase V in further, IB will increase, but IC will no longer increase. No? So we can also do a plot of IC versus IB. Okay. So when it is in active mode, okay, so you start from cutoff. When it is in active mode, this is a straight line. No? This is the expression for IC equal to beta IB. But at some point, okay, further increasing IB will no longer increase IC. And that happens here at IC sat. That happens at IC sat. Okay, so up to here, you can still apply IC is equal to beta IB. No? But beyond this point, IC will just stay at IC sat. No? Now, when do we get 48 microamperes? No? You can determine the Vin at which this will occur. No? So this occurs when Vin is equal to when Vin is equal to 48 microamperes multiplied by RB 10K, okay, plus 0.7 volts. No? Where does that come from? Well, that comes from this, no? 48 microamperes is equal to Vin minus 0.7 over 10K. No? Vn minus 0.7 over 10K. No? So, and what is this? This is 1.18 volts. No? So we know that this point here is 1.18 volts. Okay, so that's how your transistor behaves. So here, in this example, I showed you the transistor being at cutoff, no? Where your Vout is just equal to VCC. In active mode, where your Vout is equal to 2 volts. And in saturation mode, where your Vout is 0.2 volts. No? Actually, when Vn is 1.18 volts, as we computed here, no? Your output is already equal to 0.2. And increasing Vn further, while that will increase IB, will no longer increase IC. IC will stay at IC sat, which we computed to be 4.8 MA, and your V out will just stay at VCE sat. So that is the first part of my lecture on BJTs. Okay, we're going to continue on some different applications of the BJT in the next part. Thank you.